Hello, everyone. My name is Karnendu Pattanaik. I work as a senior manager in unstructured and secondary storage engineering department of Dell Technologies. Today, me and my colleague Somesh Joshi, we will be discussing about streaming data platform. We'll discuss what is the streaming data and what are all the platforms that is available in market right now, and what are all the common features. And then we will focus on one of the data platform, that is Pravega, and about its architecture, how it works, and what are all the different offerings it has, and what are all the unique features it is having. And then we will have a demo of two of the feature of Pravega in this discussion today. So moving forward, what is a streaming data platform? So before that, let's understand what is a streaming data. So streaming data is the data, it's a small chunk of data which get generated continuously by thousands of data sources, and then it gives a meaningful data chunk to store with. So in this streaming data, it could be generated by the web application or even the commercial e-commerce kind of applications, or even the mobile. Now, in current scenario, when the data type is actually changing day to day, so the technology to store this data is also changing. So this is this platforms which actually gives us the ability to store this kind of streaming data or run some analytics on that. So those are called as data platform. And modern data needs like media platform, data streaming has been become a very prominent technology. Some of the data streaming platforms are Kafka, Pravega, Pulsar, and this gives a very unique feature of streaming platforms, which is very different from the conventional storage platforms. Some of the common offering or some of the common feature that we usually see in the data streaming platforms are event streams, transactions, durable data storage, and long-term retention. Now, what are these terms? Let's understand one by one. So event streams. So basically, event is the small chunk of data that we just discussed, and then by continuously getting into one of the data structures, so this creates a pipeline of data. So that is called as a event streams. And then coming to transaction. So in transaction of data, the data which is having a sequence, or we can say a end-to-end meaningful data sequence. If we consider one of the sequence of that out of that particular data is removed, then it has no meaning. Let me give one example. So let's say, suppose one user is trying to book one movie ticket. So for that, a user has to first choose a movie name and then a theater, and in that theater he will book for the particular seat, and then he will try to do the payment transaction for that. Let's say in this sequence, at the end, the payment is not happened properly, or it got failed. So does that mean that the entire sequence data will be stored? No. So the data sequence will be, the entire transaction will be rejected. So this is the benefit of considering the data end-to-end data event data as a transaction, is that it can be accepted or rejected by by the state of one of its data sequence. Similarly, the durable of data storage. So in a particular streaming platform, what happens is these are actually multiple tier data storage happens over there. So in durable data storage basically is where it will have the current data being stored in tier 1 storage equipment, the tier 2 data can be stored in the secondary storage equipment. So that actually gives a durability of data storage because it can be accessed at the same time that data is getting stored. Also, for the historical purpose, it can be retrieved the data. Similarly, the long-term retention. So long-term retention is also, based on the similar principle that, basically the second or the older data or the historic data is actually getting stored in the tier 2 storages. So it can retain over there, and, the space management can happen properly over there. So these are some of the common feature that we get from the streaming platforms. Apart from that, there are also some of the unique feature or different additional feature which is provided by some of the streaming platform, and Pravega is one among them. So let's see what are all the additional feature Pravega offers. So in Pravega, we have something called as a auto scaling, key value tables, high partition counts maintenance, and then a consistent state of replication, ingestion of large data, and support for analytical tool. Auto scaling is a feature where the stream segment gets enhanced or decreased by the payload of the IO that is coming for that particular segment. So auto scaling is one of the feature where we are going to see the demo, and that time we will go in a detail into that. The other one is the key value table. So as we know that in key value table concept, always there is a key, and for each key there will be a value is tagged into that. So Pravega, though it has already a event based calculation as also, but still it also provide the key value tables which enables it to run a multiple analytical operation on the selective data. Operations like upgrade or delete or modify on the key set itself or the value set itself. So there could be several analytical operation done in that. And high partition count maintenance. So as we know that auto scaling is there supported in Pravega. So those partitions where there are multiple partition in the same segment happens, that is very efficiently managed over here. The other one is a replication consistent. Pravega gives one feature called as a exactly one-time semantic. So in that, whether the data is getting failed in between, but it will guarantee that one time exact one time delivery will happen to that. That means, let's say suppose data is getting failed in a transaction. Let's take a simple example here. So let's say suppose one particular transaction, financial transaction is happening. So everything is done, a user is purchasing something, and at the last moment when payment is done, so gateway also has given confirmation, but while sending the server it get failed. So in that way we do not want and the multiple copies or multiple acknowledgement to be sent, otherwise that could be a loss in data. So here the replication is consistent because it will send exactly one copy to the destination. Similarly, the ingestion of large data. So Pravega supports large data like video, where it is a very large data. It could have the capability to ingest the larger data to the data pipeline. And then the support for analytical tool, as we discussed, that's because it supports the key value table, so it has a support for the various analytical tool as well. Now, to understand what is Pravega, how it works. So Pravega, it's basically a workflow engine. That means it at a backend, it can work as an engine, and on that, different kind of streaming platform can be developed or created. So it organizes the data into stream, and where the stream is durable, elastic, and append only unbounded sequence of bytes, and which gives a strong consistency with a good performance. So it has a support for different framework like Flink. It is also a pub sub messaging supportability, and it supports the data time series database like NoSQL. Now, how it works? So Pravega actually works by appending the data at the tail. So what is that is any data chunk comes, it append only at the tail, and it writes and reads the over the data over there. Once it is a become an older data, it gets pushed for the tier 2 storage, or it become the for the historic analysis, it moved to the tier 2 storage. So in that way, when we get low latency at the tail itself for reading and writing, high throughput from the historic data availability over there. And coming to what is the design principle here. So Probega is created to consider three factors, that is delayed data, data arriving out of order, and failure condition. So for all this, Probega gives exactly one-time delivery semantic. So that means one copy, exact one copy will be delivered, no matter if the data in between gets failed. So how it does it is basically it follows a different architecture called as a kappa architecture, whereas all other middleware tools or which actually follows the lambda architecture. In lambda architecture, what happens is data source goes to application directly, and then it also goes through the service serving layer. So in that, the problem is whenever the data comes through serving layer, it could be a delayed data, or it could be the older data. And also if it goes directly to application, that it might happen that the data itself is not the accurate data. So that's why the kappa architecture, which Probega follows, is making things simple, where Probega, all the data from the sources goes to Probega, and on Probega, it gives the streaming or batch application on that itself as a streaming application, and from there it goes to the user application. So there are certain unique features of Probega. So exactly one semantic, as we discussed sometime before that, it actually resumes the data sending at the time when it stops. So ensuring that exact one once the data gets delivered, and it takes care that there is no repeated data goes or out of order data arrives at the destination. The other feature, it is the Probega streams are ordered. That means the Probega, whenever the stream, even though it is actually application defined routing keys been used, and wherever there is a two routing keys been provided to two different data, but however, Probega consider those data as first, which is written as first. So that actually guarantees that even though there could be a duplicacy in the routing key, but still data will be considered in order. The other one is the distributed computing primitive. So Probega is great for distribution application, such as microservices. The reason is the state synthesizer is a part of Probega API itself. So that actually makes it very easy for the microservices to be used in that environment. So storage efficiency, Probega actually, I mean, as we discussed some time back, that it is it has been done with the data getting appended at the tail, and whereas and then it gives, it works as an engine, and then it moves the data from Probega to all other tools, whereas a different kind of middleware streaming application, they take the data, and for each of the different kind of streaming application, they have different set of tools. So let's say real time, for real time, it is Spark Flint and batch processing using Hadoop, and SDFC for the full text search. Whereas in case of Probega, it is microservices based apps, and from the source data directly, it can go to Probega, and Probega, it goes to different streaming application and batch application, and it can perform over there. So with that, I would request Somesh to explain two of the other feature and give a demo for the Probega features.
Yeah, thanks Karnendu for briefing out about the streaming application world, the common offerings and the additional features. of one of the selected streaming data platform, that is Pravega. So I'll further discuss some of the most prominent features of Pravega, which are stream autoscaling and retention. So let me share my screen. Yeah. So what is this autoscaling feature of Pravega? The autoscaling feature gives a functionality of scaling up or growing and merging or scaling down of stream segments or the partitions within a stream as per the IO workload it receives in the real time. So how does this feature works internally? It it can be explained using this relationship diagram that we have between the routing keys and the time over gradual progression. So let us consider a Pravega stream which has two segments at time t0, segment 0 and segment 1. So by default, Pravega splits the entire uh, key range of 0 to 1 between the available segments, which is 0 to 0.5 for segment 0 and 0 to 0.5 to 1.0 for segment 1. Let us consider for time period t0 to t1 the events that are hashed and mapped to this particular segment 0 and 1 continues to grow in a fashion such that at time t1 for a stipulated time interval, we see that the amount of event population that occurred over segment 1 has surpassed its defined threshold value for this auto scale event operation to get triggered, resulting in segment 1 to get split into two new segments, segment 2 and segment 3 after time interval t1. And as default behavior of scaling, the initial or the parent segments 1 has been sealed, which doesn't allows any new events to get populated within this segment. So at t1 time interval, we can consider segment 0 has been consistently uh, receiving constant amount of IO load which didn't match the defined time. Hence, there was no split operation being observed. And at time t1 interval to t2 interval, we have now three active segments present: segment 0, segment 2, and segment 3, namely, which continues to grow as per the events being hashed and populated over these segments. So let us consider now between t1 to t2 time interval that segment 0 receives more than the threshold defined event set, thus matching the condition to trigger this event scale up operation here. And hence we get two new segments, segment 4 and segment 5 here, getting created by splitting segment 0, which is then followed by sealing of the same parent segment 0 for further events. And we can consider during this time interval, segment 2 and segment 3 were receiving constant amount of data. Hence, they were not split. And according to the same design pattern, the key ranges are also again split up and divided between the new segments after T2 time interval, which are actively as segment 4, 5, 2, and 3. And the left side, we can see the split of routing key ranges. So now if we consider time T2 to T3 interval, that if the amount of data or event that is getting populated over these two segments, segment 2 and 5, is below the threshold value for a stipulated amount of time and matches this scale down condition, then it results in merging the two segments, segment 2 and 5, after time interval t3 with the creation of new segment 6 following the seal of segment 2 and segment 5 operations. So now after t3 time period, we'll be able to have three active segments only present: segment 4, 6, and 3, which are receiving continuous data, and so on. So in order to further uh, explain this feature, let me start with the demo of the same auto scaling feature on a live cluster of Pravega. So let us now observe the two workloads that are being considered here for the demo purpose. The two supported auto scaling policies are also defined for these two workloads, data-based and event-based. So the data-based at configuration level is defined as bytes per second value, whereas event-based scaling policy is defined as events per second. So if we consider this particular workload, whose stream name is medium scale, there are other stream policy configurations that can be seen: minimum number of segments, scale factor, and target rate. So the minimum segment value defined 4 indicates that when the stream gets created, it will have at time t0 4 number of segments. The target rate here defines 200 value, which means if the IO workload that is generated or gets populated over the stream segments for the stream crosses 200 event per second value, then this stream segment will experience scale up event operation by a scaling factor value of 2 multiplied. That means the initial minimum segment value 4 becomes 8 if the target value has been matched after a stipulated amount of time. So the same condition holds good for byte-based scaling policy, where we have defined same 200 value here, but the unit for bytes per second is kilobytes per second. So that means if the IO workload that is appended for stream segments uh, defined with the scaling policy reaches or crosses the target rate of 200 kilobytes per second for a period of time, considerable period of time, then its minimum segments gets multiplied by its scaling factor, resulting to scale up event operation. And the scale down operation is in the reverse manner, following if the target rate falls, if the current IO rate falls below its target defined value, then the current segment value will get merged or reduced by the same scaling factor up to minimum value 4, not below that, which holds good for both the plans here. Now let me demonstrate the same uh, feature at the live cluster level, where we can see from the metrics the two different plans that I had explained here, medium scale and medium scale bytes. These are the two workloads for which we have defined the same configuration of scaling policy. And if now we observe the metrics, we can see that the initial segment value that was created for the stream was 4, and a considerable period of time, which is a condition of scaling here. And for any new stream, the last condition holds true, which is if the 10-minute rate is greater than the target rate for that segment, then scale up event operation is triggered. And similarly, if the 10-minute rate is lower than the target rate value, then scale down event operation is triggered. So from the metrics, we can observe at 1949, this stream was created with 4 segments, And after next 10 minutes, since the number of events per second value we can see from this graph here was 4,000 events rate during the first 10 minutes, which is obviously higher than the defined 200 value. So we can see immediately after 10 minutes, there was a split of segment that occurred here. And the initial 4 segments got split into 8 segments. Similarly, we have other plans, medium scale DX bytes, which I had explained had bytes per second scaling policy been defined, that is data-based scaling policy. And the target rate here is 200 KB per second. So if we observe the graph here, the same stream was also created at 1948 time, and the byte per second rate which it was observing during its creation was 967 KB per second, which is obviously more than the target rate 200. And hence, just 10 minutes after its creation, 1958, there was a split by the same segments being observed, multiplied to its scale factor value 2, and we got 8 segments running. So as we can see from the graph here, the IO workload that has been appended per segment level here gets reduced by each segment split that occurs. So this also demonstrates here how Pravega manages the continuous IO workload here by the auto scaling feature, which distributes the IO workload further among its available segments by the cooling or the heating effect of the segments, which is very helpful for dealing with the practical implementation of a streaming application. So now I'll proceed with the next unique feature of Pravega that we are going to discuss here, which is retention. And what does this retention feature here offers us? So the user has the advantage of real-time processing of data, while uh, is also benefited with the historical data which is present on a tier 2 level of storage. So how does the user gets an unlimited retention advantage here? If no retention policy or limit has been set for the configured stream over which data will be populated, then the data can reside over the same stream for infinite period or of time until the storage doesn't runs out, the underlying storage. So on the same end, user also has the feasibility of setting time-based or size-based retention bound policies that will ensure that the data resides over the stream for its configured time period or the size value. So accordingly, if a time-based retention has been set, then the data resides for a specific limit of time. And if the retention or the truncation cycle occurs and the data crosses the limit of time, then yeah, that will be truncated. The same applies for size base. So on a more practical understanding of this features implementation at Pravega side, let me now start a demo on the same area. Hello everyone. This is the stream name test size retention and the scope name for which I'll be demonstrating size-based retention policy of Pravega. The stream has already been created on our deployed cluster, and the initial record size before the first stream cut, that is at interval T0 to T1, is 2.4 GB. The number of records been written to the same stream during this interval are 30,000 records. I'll note down the same data here. 2.4 GB of data in the interval T0 to T1 was gathered, and it is before S1, the first stream cut. So the retention cycle is been set here for 30 minutes. So after every 30 minutes, there will be a stream cut which will be performed on this retention policy set stream. And now the first stream cut time has already surpassed. And from the logs of this test, we can observe the second stream, the first stream cut has already taken place, and we have written some additional set of records over this in order to qualify the stream for truncation over this set size limit value. So the new set of records that we have written here is 9,000. Let us see, do we observe any size change after the new records been written? Yes. So now the new size after stream cut 1 is 3.1 GB. So let's record the new data. So this is between time duration T1 to T2, which is after stream cut 1. That means we have written some additional 600 MB of data nearly, which is obviously higher than the limit size been set, that is 488 MB. So we expect after the stream cut 2 takes place, we will be truncating the extra data here and would be retaining the remaining data above the size limit. So let us now again read the records over the same size-based test retention stream, having this as the scope name and the stream name. So the reads has been completed over the same existing size-based retention stream, and we see an increase in the record size from the initial 30,000 value. So 9,000 additional records has been written during the period T1 to T2 after stream cut 1, which has surpassed the set size limit value, that is 488 MB. And now we expect after the next retention cycle, that is after 30 minutes, that the extra amount of records been written would trigger the truncation operation over the stream, resulting in size reclamation or retention of the remaining records over the limit. So now the time has been passed when the second stream cut has to be taken, means the second retention cycle has crossed over. So now we will see what is the new size limit, size of the records that is being holded by this test retention stream under the scope. $844 MB. So this is the thing. We are able to witness the truncation of data occurring over here. And how did it occur? I'll explain it further. Parallelly, I'll also make a read request to the same stream in order to identify what is the new count of records that are present over this stream after truncation occurring. So from the logs of this test, it is very evident that after the second stream cut getting completed, we were able to read only the new or the extra records been written after stream cut 1, that is 9,000 records. The read request is continued. Let me explain, let me record the new data first, and we can evaluate the logic. So this is the new record in the time frame T2 to T3, which is after S2. So these are the total records. Now let me explain how interestingly Pravega identified the surplus data and the truncation took over. So there's a fascinating way of comparing the data over here. Each time a stream cut record, uh, each time the retention cycle executes, a stream cut record is created. So during this time frame, S1 had initially 2.4 GB of data, but after the next retention cycle at S2, when the new record size was calculated, it happened to be 3.1 GB. So immediate to the next stream cut being taken, Pravega identifies that there is a surplus record been written by differentiating between these two stream cuts, S2 minus S1. So the new set of records, 9,000 records that we had written earlier, becomes the additional data, and now this data which was over the size limit been set, the truncation was triggered, and hence the initial data which we holded during S1 was truncated, leaving us behind only the new set of data. So the reads have also been completed. Hence, the latest read records shows us only 9,000 records now reside on this stream, which were earlier in the very first read attempt, there were 30,000 records, and then we additionally wrote 9,000 records, which summed up to 39,000 records. And post stream cut 2, when the truncation occurred, the new record set is only of 9,000 events. So this is how Pravega achieves size-based retention, and there might be some additional data that we see more than the surplus, that is the accumulation of its metadata. So hence, with this, I conclude the demonstration of size-based retention policy of Pravega. Thank you.
Thank you, Somesh. It was a wonderful demo, and it shows how Pravega works in real-time cluster.
Thanks, Karnendu.
Okay, so while preparing this demo and the content, we have taken reference from different websites. These are our reference point. With this, we are open to Q&A.
Thank you, everyone.
Thank you, everyone.